This is John Whitaker for the Mathematical Analysis 2 class, and this is our 4th video lecture. And we're still working with differentiation, and today we want to start off with something called the Cauchy mean value theorem. And here's what it says. Again, it's called the Cauchy mean value theorem. Cauchy mean value theorem. And it says that if f and g are continuous real functions on a to b, which are differentiable in the open interval from A to B, then there exists an x that's in the open interval from A to B, at which f of b minus f of a, that quantity times g prime of x, will be equal to g of b minus g of a times f prime of x. So we want to prove this. So we let f and g be continuous real functions, meaning their output values are real numbers, on the closed interval for A to B, which are differentiable on the open interval from A to B. Okay. Now, to get the conclusion, we want to find an x in the open interval from A to B such that f of b minus f of a times g prime of x is equal to g of b minus g of a times f prime of x. And in order to find that x, we're going to consider a function. We're going to consider the function h of t equaling f of b minus f of a times g of t minus g of b minus g of a times f of t. Okay. Now, what we're going to notice about h is that since g or let's say, since f and g are continuous, on closed interval from A to B, then that will force h of t to be continuous. On A to B. Similarly, since f and g are differentiable, on an open interval from A to B, then h will also be differentiable on A to B. In fact, we can compute the derivative of h at t for t in the open interval from A to B. So what we have is we have f of b minus f of a times g prime of t, and it would be minus g of b minus g of a times f prime of t. So that's what we have with the derivative. Okay. The thing to notice about the derivative of h prime, the derivative of h of t, I should say, is that from what it's equal to, if there exists an x element of open interval from A to B with h prime of that x equal to 0, then we have okay, 0 equals to h prime of x, and if you remember what h prime of x would be, it would be f of b minus f of a times it's g prime of x minus, here it's g of b minus g of a times f prime of x. Okay, that's what we have. And so that's equal to 0. So if I pull this to the other side, then, which would imply that g of b minus g of a times f prime of x would be equal to f of b minus f of a times g prime of x, which is what we're trying to show. So we're looking for an x element of A to B such that h prime of that x is equal to 0. That's what, so let me write that down. See if we can show there exists an x element of the open interval from A to B such that h prime of x is equal to 0. We have proven the theorem. Okay, so now we're going to show that h prime is 0 for some x in open interval from A to B. Now, here's the first thing we'll note in this process. If you look at what h of A is, it's equal to f of b minus f of A times g of A minus, and then here it is g of B minus g of A times f of A. And then if we multiply this out, we're going to get this f of B, g of A, minus f of A, g of A. And then this is minus g of B, f of A, minus, a minus makes a plus, g of A, f of A. And here, these two guys have the same signs, we cancel with each other. And so what we're left with is f of B, g of A, minus g of B, f of A. That's what we get. All right, now let's also observe what f evaluated at B is. So this is what h evaluated at B is. This will be f of B minus f of A times g of B minus g of B minus g of A times f of B. And then when we distribute, simplify, we have f of B minus, times g of B minus f of A times g of B, and then this is minus g of B times f of B, and then here will be plus g of A times f of B. Okay, in terms of simplification, these two quantities are the same. And so what I'm going to write down here is this quantity first, which is g of A, f of B. So these two guys are going to cancel with each other. It's minus f of A, g of B. Now if you compare this line right here to this line right here, you see they're the same. So that says that h of A and h of B are equal. So, as I said, h of A equals to h of B. So, that's going to allow us to consider two cases for h of t. For h of t. You see, h at the endpoints of this interval, h at the endpoint of this interval are the same. So maybe the function h of t is constant over that interval. So that's case one. What we have found, though, if you give me a function that's constant, it's differentiable. We already knew h of t is differentiable on the open interval command. Then h prime of x, or h prime of t, I would say, equals to 0, and that's true for all t in the open interval from A to B. So for any x, element of A to B, h prime of x will be equal to 0. Remember, we're just trying to show the existence of some x in the open interval from A to B such that the derivative of h at that particular x is equal to 0. And in this case, there's tons of x's that make this true. And that was sufficient to show that the theorem is true. So if the theorem is true in this case, where h of t is a constant. In case 2, let's say h of t is not a constant. Okay, since we go back to analysis 1 here, we have proven that the closed interval from A to B is compact in R, and we've also shown that any real function, so any real value function on a compact set attains both its maximum, absolute maximum, I'm going to write down absolute. And absolute minimum. Then H attains its absolute maximum and absolute minimum. On A to B. Well, since in this case H of t is not a constant, and H of A is equal to H of B, then H of t must attain either its absolute max or absolute min at an x that's in the open interval from A to B. It can't be at the endpoints for both of them, okay? For both absolute max and min, because they were the same, and H of t is not a constant function. Okay. In other words, what we just said was, thus, there exists an x element of A to B such that H of x is either an absolute max or absolute min. Since H of x, H prime of x exists by a previous theorem, then we know this exists because of our supposition about f and g being differentiable in the open interval. Then, if we're looking at a maximum or minimum, they're absolutely going to be local too, then H prime of x will be equal to 0 from a previous theorem. And that's what we needed to show, is that H prime of x equals to 0 for some x in the open interval from A to B. So in all cases, there exists an x element of the open interval from A to B such that f h prime of x equals to 0. So at that particular x, we know that f of b, I'll say it this way. So there exists an x element of A to B such that f of b minus f of a times g prime of x is equal to g of b minus g of a times f prime of x. And that concludes the theorem. So that's the Cauchy mean value theorem. We're going to use this Cauchy mean value theorem to prove something called the mean value theorem. And that's what's next. Okay. So here's the theorem. It's called the mean value theorem. When it says if f is a real continuous function on the closed interval from A to B, which is differentiable on the open interval from A to B, then there exists an x element of A to B such that f of b minus f of a will be equal to b minus a times f prime of x. So this is, in a sense, a corollary to the Cauchy mean value theorem. Okay? Here's why I said it's kind of correlated. It can be seen in the proof. So we'll just go ahead and get started with the proof. That's left f be a real continuous function on A to B, which is differentiable on the open interval from A to B. Okay. Let us examine another function, g of t, which will let b equal to t. If we define it on A to B, is continuous on A to B and differentiable on G of t is on the open interval from A to B. So, by the Cauchy mean value theorem,
there exists an x element of A to B such that f of B minus f of A times g prime of x equals to g of B minus g of A times f prime of x. That's by the Cauchy mean value theorem. Okay, so what do we have? We have f of B minus f of A. Now g prime of x, well g of t is equal to t. Its derivative is 1. So g prime of any x value is going to be equal to 1. And this is going to be g of b, which is going to be b, because g grabs whatever, it sends it to itself, minus a, and here's f prime of x. And that's exactly what we're going to, what we wanted to show. So that is the theorem. Another way of looking at this is we could say f prime of x, and this is the way a lot of texts write the mean value theorem, that there exists an x such that the derivative evaluated at that x is equal to f of b minus f of a all over b minus a. So that's the end of the proof. The way that I have rewritten the statement there at the end for the mean value theorem, it corresponds with a picture. So here's the idea of what this theorem is saying pictorially. We're going to concentrate on f prime of x equaling to that, on that right-hand side, equaling to that f of b minus f of a all over b minus a, which I've written there in that bottom corner. Pictorially, what's being said here? You have some kind of prototypical function f. This is my f. Here's a, maybe here's b. And so this is f of a. Right here maybe is f of b at y value. Look, f of b minus f of a all over b minus a is nothing more than the slope of that line. Okay? The slope of the line connecting those 2 points. And what we're saying is there's some x in an open interval from a to b, at least one, such that the derivative of this function at that x, so say right in here, is the same as the slope of this line. So we're saying the slope of the curve, because that's what the derivative can represent, is the same as the slope of the line at some point. The slope of this curve at some point is the same as the slope of this line connecting those 2 points. That's what the mean value theorem is saying. Okay, well, we can use this now to talk about a relationship between derivatives of real value functions and whether they are increasing or not. This is a theorem you probably remember from calculus. Here's what it says. It says, suppose f is differentiable f is differentiable. Let me write this down here. In A to B, so we got 3 parts. First part is if f prime of x is greater than or equal to 0 for all x in an open interval from A to B, then f is monotonically increasing. On Well, we're going to have similar statements about whether the derivative is constantly zero or negative. So let me write those up. Part B, if f prime of x equals to 0 for all x in a to b, then f is a constant. Part C, if f prime of x is less than or equal to 0 for all x element of a to b, then f is monotonically decreasing. On a to b. We're going to prove parts A and B, and part C, I'm going to leave for you to prove, and it'll be like part A. Okay, so here's the proof. In general, we're going to suppose f is differentiable on open interval from A to B. And then part A, we're going to suppose for all x element of the open interval from A to B, f prime of x is greater than or equal to 0. Okay. We want to show that f is increasing. Okay, how are we going to show that f increases? So we write that down, and we want to show f is monotonically increasing on A to B. Okay, well, what we're going to do that is to show that a function f is monotonically increasing on this open interval. We're going to take 2 points within that interval, x of 1, x of 2, x of 1 being less than x of 2, and we have to show that f of x of 1 is less than or equal to f of x of 2. Let me write that down. We're going to let x of 1 and x of 2 be an element of A to B with x of 1 being less than x of 2. Okay? And then we want to show, this is exactly the requirements of the definition for monotonically increasing. We want to show f of x of 1 is less than or equal to f of x of 2. Okay? Now, the thing we're going to turn to first is that since f is differentiable, on A to B, then f is differentiable on the closed interval from x of 1 to x of 2, which of course is contained in A to B. Okay? So what that means then, we can also say it this way. Differentiability, we learned, implies continuity. So I'll write this out. So we have f is continuous on x of 1 to x of 2 and differentiable on open interval from x of 1 to x of 2. So by the mean value theorem, applied to f, oops, I got excited. Forgot to change the board. Okay. So what we said was that f is differentiable on the closed interval. Differentiability implies continuity. So f is continuous on the closed interval from x of 1 to x of 2. And it's differentiable on the open because it's really differentiable including at these endpoints on the closed. So by the mean value theorem, there exists a y element from x of 1 to x of 2, open interval, such that f of x of 1, f of x of 2 minus f of x of 1, so that's the role of b and a here, will be equal to x of 2 minus x of 1 times f prime of y. Now, since x of 2 is greater than x of 1 and f sub prime of whatever, I'll write down x, is greater than or equal to 0 for all x element of, well, here it would be x of 1 comma x of 2, because we had it from a to b. Then this is greater than or equal to 0, this is greater than or equal to 0, so this is going to be non-negative. Then that means that f of x of 2 minus f of x of 1 has to be greater than or equal to 0. So that says that f of x of 2 is greater than or equal to f of x of 1. And that's what we wanted to show today. Let me write the conclusionary statement. So f of x is monotonically increasing. That proves part A. Now for part B, we're going to let f prime of x be equal to 0 for all x element of a to b. We want to show f is constant. Okay. Well, let's let x of 1 and x of 2 be element of a to b, with x of 1 being less than x of 2. We want to show f of x of 1 to be constant, for f to be constant. Better be equal to f of x of 2. That's what we need to show. Now, again, note f is differentiable x of 1 to x of 2 closed. And that's going to imply that f satisfies the conditions of the mean value theorem on the closed interval from x of 1 to x of 2, just like what we said before. So, by the mean value theorem, there exists a y element of the open interval from x of 1 to x of 2 such that will satisfy the conclusion of the mean value theorem. Such that f of x of 2 minus f of x of 1 is equal to x of 2 minus x of 1 times f prime of y, which you get. And now what we know is this part is 0. So we have f of x of 2 minus f of x of 1 equals 0, and f prime of y is equal to 0. This part's 0. 0 times something is 0. So this part must be equal to 0. So that means that f of x of 2 equal to f of x of 1. And these were just arbitrary numbers in A to B, and so we're saying that the output values are always the same, so f is a constant. That ends the proof for part B. For part C, this will be a homework problem. And the proof is analogous to the proof in part A. Proof of part A. That's what we have. I won't do that. We'll leave it for you to do. Okay, what we'll end with is one more theorem and proof, and here's what it says. It says, suppose f is a real differentiable function on the closed interval from A to B, and suppose f prime, let's write it, f prime of A is less than some number lambda, which is less than f prime of B. Then there exists an x in the open interval from A to B such that f prime of this particular x will be equal to lambda. And this theorem can be thought of as, or entitled, the intermediate value theorem for derivatives. And what it's saying is that if you give me some number in between f prime of A and f prime of B, there's some number in between there, then there's some spot in between A and B such that the derivative attains that number. The derivative function here. So even though the derivative might not be continuous, it's going to get to every number in between f prime of A and f prime of B. Now, before I go to prove it, let me just say that we can say a similar statement is true if we have f prime of A is bigger than any particular number, which is bigger than f prime of B. Okay, so let's prove the statement we have. Let's put g of t equaling to f of t minus lambda times t. Not lambda of t, lambda times t. Okay? So let's look at g prime evaluated today. Well, that's going to be equal to f prime evaluated today minus lambda. Now, what we know in the situation we're looking at is that f of A is less than lambda, so this is going to be negative. Okay. So less than 0. So, that's going to say that the limit as t goes to A from the right of g of t minus g of A, I'm going to apply this, all over t minus A, this has got to be less than 0. Okay. What that's going to imply, so here this is g prime of A right here. So that implies that there exists a t sub 1 element of A to B such that let's see, now t is bigger than A, so g of t g of t sub 1 has to be less than g of A for this statement to be true. Well, we could say a similar statement involving g of B, and we will. Similarly, g prime of B, which equals to f prime of B minus lambda, is going to be greater than 0. So that means that the limit as t goes to B from the left of g of t minus g of B all over t minus B is going to be greater than 0. So there exists a t sub 2 that's an element of the open interval from A to B. Such that g of t sub 2, okay, let's see, this is negative, so this also must be negative. So g of t sub 2 minus g of B is going to be less than 0. So this is going to be less than g of B. Since g is differentiable, A to B. G is continuous. On A to B. And here I'm closed. Which we notice that this closed interval is compact. So that means that G attains its minimum on A to B. Now, our previous work, what it's shown with those G of T sub 1 and G of C sub 2, it shows that G of A and G of B are not minimums. And so since they're not, there exists the next element of A to B such that G of X is a minimum. So what that means is G prime of X, which if you remember the way that G is defined, is F prime of X minus L. Well, look, when you have a minimum, you have a minimum or a maximum, the derivative, and the derivative exists, and here it does, then that derivative is going to be equal to 0. So that's what we have here. So that says that F prime of X must be equal to L. And that is the theorem. Well, ladies and gentlemen, that is enough for this video lecture. I want to thank you very much for your time and patience.